Welcome back to the Deep Dive. I was driving in here today, relying entirely on the blue line on my dashboard to tell me where to turn, how fast to go, and when I'd arrive.
We all do.
We all do. And it hit me, we act like this connection is permanent, like the internet, the GPS signal, the ability to tap a credit card. We act like it's as natural as the air we breathe.
It feels like a utility, like water or electricity.
Exactly. But looking at the stack of documents we have today, I'm realizing that the now we live in, it's incredibly fragile.
It is. It really is. We treat infrastructure like it's geology, like it's made of stone and can't move. But the reality is, modern civilization is built on a very specific, very delicate frequency.
And when that frequency drifts, even by a millisecond, things start to break. We aren't just talking about your Spotify buffering.
Oh, not at all.
We're talking about the power grid desyncing. We are talking about financial markets crashing because the timestamps on trades don't match up.
Exactly. And that fragility is the starting point for everything we are digging into today. We have a stack of documents here from a company called T.L.TEDFORD Enterprises.
All right.
And if I'm reading this right, and we are going to go through this with a fine-tooth comb, they aren't just trying to patch the system we have. They are trying to build a backup hard drive for the entire planet.
A backup hard drive for the planet. That sounds like science fiction. I mean, we've got terms in these papers like quantum sensing, living ground mesh, and acoustic networking.
The buzzwords are definitely there.
They are. But the crazy part is, mixed in with all this high-tech wizardry, we have a very boring, very blurry screenshot from a government website that suggests this is actually happening.
That screenshot is my favorite part of the stack. It really is. Because anyone can write a white paper about quantum mechanics and saving the world. But getting a government subcontract report number, that is where the rubber meets the road.
Okay, so our mission for this deep dive is to connect those dots, to understand the tech, which they call the node, to look at the validation, which involves, strangely, the Royal Navy, and then to get into the administrative reality of that sam.gov document.
That's the plan.
We're going to get to that screenshot, a sam.gov document later on, and we're going to dissect it line by line. But first, we need to understand the problem they are solving. One of the documents is titled the AI Quantum Infrastructure Disclosure Framework. It starts with a pretty heavy section called the Global Problem Humanity Faces. It's not exactly light reading.
No, it's not. It's a wake-up call. The document essentially argues that humanity has put all its eggs in one basket. Centralized systems. Think about GPS. It's a constellation of, 30-something satellites orbiting the Earth? It's amazing technology.
It's a miracle it works at all, really.
It is, but it's miles away in space. And space isn't as empty as it used to be.
By a long shot.
Right. You have debris, you have solar flares, you have the potential for conflict, what they call congestion and interference. If you lose that signal from the sky, even for a few minutes, the systems on the ground are blind. The document calls this a failure of legacy infrastructure.
It's terrifying to think about. I mean, if Google Maps goes down, I'm annoyed. Maybe I'm late. But if the timing signal for the electrical grid goes down...
Then you have rolling blackouts. Best case. If the timing signal for the banking system goes down, you can't verify transactions. The premise here is that we are relying on a signal that is too far away and, frankly, too easy to block.
So enter T.L.TEDFORD Enterprises. They're proposing a solution that sounds almost biological. They call it a living ground mesh.
The word living is doing a lot of heavy lifting there, but it's an accurate description of the architecture. Instead of a top-down system where a satellite tells everyone where they are, they are proposing a bottom-up system, a network that lives in the dirt, in the pavement, in the cars, and even underwater.
So instead of looking up at the sky to find out where you are, you're asking the ground.
In a way, yes, you are asking the environment around you.
Okay, let's unpack the actual hardware. Because when I hear infrastructure, I picture giant cell towers or fiber optic cables being dug up in my front yard. But I'm looking at this document titled Core Operational Unit of the Global Living Mesh, and it doesn't look like a cell tower.
No, and that's the first paradigm shift we have to wrap our heads around. This is what they call edge intelligence.
The edge. I hear that buzzword at every tech conference.
It is a buzzword, but let's define it in this context. Usually, the cloud is the sender. Your phone collects data, sends it to a massive server farm in Virginia. The server thinks about it and sends an answer back. That's cloud computing.
Right. The big brain in the sky.
The big brain in the sky, edge computing, is doing the thinking right where the data is collected.
So the brain isn't in Virginia. The brain is in the device.
Exactly. And the T.L.TEDFORD node, that's their core unit, is a self-contained intelligence unit. And the most important feature listed here is that it is hardware agnostic.
Hardware agnostic. That sounds like a fancy way of saying, we'll put it anywhere.
That is exactly what it means. And think about the business implication of that. If you are building a self-driving car, like a Tesla, you are building a closed system. You want your car to be the smartest thing on the road.
Right. It's your own private ecosystem.
T.L.TEDFORD isn't trying to build the car. They want to be the nervous system that the car plugs into. The document says this node can sit in an electronic control unit, ECU, in a vehicle, in an aviation unit of a drone, in a mobile device, or embedded in the pavement itself.
Embedded in the pavement. So in theory, my car could be a node. The streetlight could be a node. The drone delivering my pizza could be a node.
Yes, and because they are all nodes, they are all speaking the same language. They create a mesh. But before we get to how they talk to each other, we have to talk about how they think. Because there is a phrase in here that I absolutely love: physics over AI.
I circled that too. In a world where every startup is pitching generative AI this and large language model that, it's weird to see a tech company saying, no, we prefer physics.
It's not just preference, it's a safety requirement. Think about how a large language model works. It guesses the next word in a sentence based on probability. It's amazing, but it can hallucinate. It can be confidently wrong.
We've all seen chatbots make up facts, just confidently state something that's completely untrue.
Right. Now imagine you are doing 70 miles per hour on a highway. Do you want your car's safety system to guess based on probability?
Absolutely not.
Or do you want it to know based on physics?
I want the physics, please. 100%.
Exactly. The Tedford node uses time-to-collision metrics. It's calculating velocity, mass, vector, and friction. It's not asking an AI what does a crash look like. It's calculating object A is moving at speed X and will occupy the same space as object B in 0.4 seconds. That is physics. It is non-negotiable.
The document mentions trust and guardrails. It says the system is architected to refuse false certainty. That's a powerful phrase.
It is a profound concept for an automated system. Refuse false certainty. It means if the sensors are getting conflicting data, maybe it's raining hard or the sensors are muddy, the system won't just pick the most likely option and hope for the best.
So it won't just shrug and make a guess.
It will explicitly say, I do not know.
And then what? It just gives up? Does the car just pull over?
It engages human-first alerting. It uses audio, haptics like shaking the seat or steering wheel, and visual cues to snap the human back into the loop. It basically says, I have lost certainty, you have the con.
That feels surprisingly humble for a piece of tech. Usually the pitch is, sit back, take a nap, the car has got this. This is saying, the car has got this until the laws of physics get fuzzy, and then you better be awake.
Which, if we're being honest, is the only responsible way to deploy autonomy right now. But the real deep dive aspect here is what happens when everything else fails. The degraded mode.
The zombie apocalypse scenario.
Essentially, yes. The document asks, what happens in a GPS denial scenario?
We see this happening in conflict zones right now. Jamming signals is, a standard tactic.
It's day one electronic warfare. If you jam GPS today, most drones just drift away or crash. They lose their place in the world. The Tedford node switches to something called dead reckoning.
Okay, I have to stop you there. Dead reckoning. It sounds incredibly ominous, like something from a pirate movie.
It does sound cool, doesn't it? But it's actually an old nautical term. It stands for deduced reckoning. If you are a sailor in the 1700s, and it's cloudy so you can't see the stars, and you are in the middle of the ocean so you can't see land, how do you know where you are?
You guess, you pray.
You calculate. You know where you started. You know how fast you've been going. They would throw a log over the side on a rope to measure speed. You know your compass heading, so you do the math. I started at point A, moved east at 10 knots for 2 hours, so I must be at point B.
But that's incredibly prone to error. If you make a mistake in the math or the current pushes you,
then your reckoning drifts. You get lost. That's the classic problem. But the Tedford node does dead reckoning with modern sensors. It measures the rotation of the wheels, the acceleration forces from its inertial measurement unit, the turn of the steering wheel. It calculates its position locally without needing a satellite to tell it.
But wouldn't it still drift eventually? Like the sailor, the errors would accumulate.
Yes, over time, it absolutely would. A single node on its own would eventually get lost. But that is where the mesh comes in. This is the peer signaling mentioned in the source.
Peer signaling. So the nodes talk to each other.
Imagine you are that sailor, blindly calculating your position. But imagine there are 1,000 other ships around you, and you can yell to them, hey, I think I'm at coordinates XY, and the ship next to you says, I think I'm at XZ, and the ship next to him says something else.
You compare notes, you find the average, and assume that's closer to the truth.
Exactly. You crowdsource your reality. The local heuristics allow the network to consensus check itself. We can't all be wrong in the exact same way. So the mesh tightens up the accuracy and corrects the individual drift of each node.
So even if the sky is dark, metaphorically or literally, the cars on the road are whispering to each other to figure out where they are.
That's the living ground mesh. It's resilient because it's distributed. There's no single point of failure.
Let's move to section 2, the architecture. Because it's one thing to have a smart box, it's another thing to connect millions of them into a global network. The document calls this the transceiver repeater fabric.
This comes from the letter to Dr. Eva Muller-Stoller. It's dense, but the core idea is distributed mesh over isolated endpoints.
Unpack that for me. Isolated endpoints.
Okay, look at your phone. Right now, it is an isolated endpoint. It speaks directly to a cell tower. If that tower goes down, or if you go into a tunnel where the tower can't see you, you are cut off. You are isolated.
I become a brick. A very extensive brick.
You become a brick. In a distributed mesh, your phone wouldn't just talk to the tower. It would talk to my phone. And my phone would talk to the laptop over there. And the laptop would talk to the smart fridge. And eventually, one of those devices, maybe the fridge, has a connection to the tower.
So the signal hops.
Yeah.
Like a bucket brigade passing water from the well to the fire.
Precisely. The document calls them gateway nodes. These are the specific nodes that have a view of the sky or a hardline connection. They act as the bridge, but everyone else just needs to see each other.
So you could have a string of cars going deep into a tunnel. The car at the entrance can see the sky. The car in the middle can't. But because they are daisy-chained, the car in the middle still gets the signal.
Yes, the signal flows through the mesh. This is why they claim it works in urban canyons, those city streets where skyscrapers block the GPS signal. Or in dense jungles. You don't need to see the satellite. You just need to see a friend who sees the satellite.
That seems incredibly robust. But then we get to the buzzwords again. AI and quantum. The AI Quantum Infrastructure Disclosure Framework puts them together. Usually when I see quantum, I assume it's vaporware.
Sure.
Or it's a computer that needs to be kept at absolute zero in a basement somewhere.
That is the traditional view. And for quantum computing, that's largely true. But this is about quantum sensing. Quantum sensors are fragile. They measure things like gravity anomalies, magnetic fields, and the passage of time with insane precision. But if you put one in a Jeep and drive over a pothole, it usually breaks.
So how is Tedford putting them in hardware-agnostic nodes that go in potholes?
They are using the mesh to stabilize the quantum. It's a brilliant concept. If you have one expensive, fragile quantum clock, it's risky. But if you have thousands of cheaper, slightly less perfect sensors and you network them.
The crowdsourcing again, you're averaging out the noise?
Right. The mesh acts as a stabilizer. If one sensor drifts because of a bump in the road, the AI, the cognitive layer, spots the outlier. It says, hey, node 42 just reported a time variance that doesn't match the other 500 nodes nearby. Ignore node 42 until it recalibrates.
So the AI is the conductor of the orchestra, making sure no single instrument is playing out of tune.
Yes. It creates a closed loop, quantum senses the world, the mesh connects the data, and the AI validates and corrects it. It allows you to take lab-grade technology and throw it into the mud.
Speaking of mud,
Yeah.
let's talk about water. Because this is the part of the letter to Dr. Muller-Stoller that really blew my mind, the oceanic extension.
This is where the physics gets really interesting.
We've established that GPS works from space,
Mm-hmm.
and we know satellites can't see underwater.
Radio waves, which is what GPS, Wi-Fi, and 5G are electromagnetic radiation. Water is incredibly good at absorbing that radiation. It's like trying to shine a flashlight through a brick wall. The light just stops.
So submarines have always been blind. I mean, relatively speaking.
They have been isolated. To get a GPS fix, a submarine has to surface or float an antenna to the top. That's dangerous if you're trying to be stealthy.
So how does the Tedford mesh solve this? You can't just put Wi-Fi repeaters underwater.
They use acoustic networking.
Sound.
Sound travels beautifully through water, much better than it does through air. Whales have known this for millions of years. They can communicate across entire oceans.
So Tedford is building an internet of whales.
In a sense, The document describes submerged nodes, think underwater drones, or autonomous underwater vehicles, AUVs, that have acoustic modems. They chirp data to each other.
Like an old dial-up modem, that horrible screeching sound.
Very similar principle, though hopefully less grating. It's slower than Wi-Fi, but it travels for kilometers underwater. And for short ranges, like if two drones are right next to each other, they switch to optical links.
Lasers.
Lasers or flashing lights to transfer massive amounts of data instantly. So you have this layered system, sound for distance, light for speed.
And then floating on the surface, you have gateway buoys.
Exactly. These are the translators. They float on the waves, listen to the acoustic chirps from the deep, and then beam that data up to the satellites.
It connects the bottom of the ocean to the stars.
It creates a seamless fabric, and that is the goal. No gaps, no dead zones. Whether you are in a tunnel, in a jungle, or under the ice cap, you are part of the mesh.
It's wildly ambitious.
Yes.
But is it real, or is this just a really well-written pitch deck? This brings us to Section 3, Market Validation. Because we have an article here from the UK Defence Journal, dated January 30th, 2026.
Yes, the Eagle's Eye trial.
The headline is, Royal Navy tests helicopter-led drone targeting in UK first. And naturally, since it's in the stack, I thought, aha, this is it. This is the Tedford node in action.
And I hate to be the bearer of bad news, but it's not.
It's not. Why is it in our stack then?
We have to be very precise here. The source document says this was a Royal Navy trial using a Wildcat helicopter and drones like the Puma. It lists the partners involved. T.L.TEDFORD is not listed as the hardware provider for this specific test.
So why are we talking about it? What's the relevance?
Because of doctrine validation.
Doctrine validation. That sounds like military speak.
It is. In the investor materials source, Tedford points to this article. They aren't claiming credit for the test. They are claiming credit for the idea.
Explain that. That seems like a fine line.
It is, but it's important. The Royal Navy spent millions of pounds and months of planning to prove a specific point. That in modern warfare, you need a mesh. They turned that helicopter into a flying command center. They proved that if you network a bunch of drones together, they are deadlier and harder to kill than if they operate alone.
So the Navy proved that the concept of a mesh is vital for their future operations.
Exactly. They validated the market need. If you are T.L. Tedford, you look at this and say, see, the Royal Navy is desperate for this capability. They are cobbling it together with helicopters and mismatched drones. We are building the infrastructure to do this natively everywhere.
It's like seeing the military try to build their own internet in the 1960s and then walking in and saying, hey, we're building the actual internet. You can just subscribe to ours.
It moves the conversation from, is this technology possible, to who can scale it. The Navy test was tactical, one mission, one squad. Tedford is strategic national scale, permanent infrastructure. The world's militaries are basically shouting from the rooftops that they need what Tedford is building.
So the military wants it. The tech exists, at least on paper. But who is paying for it?
Yeah.
And this is where we have to put our detective hats on.
Yeah.
Because we are moving to Section 4, the SAM.gov deep dive.
This is the part that gets me excited, the paper trail.
I have the screenshot in front of me. It is tragically boring.
Yeah.
It's gray. It's a table of numbers. It's from a website called SAM.gov. For you listening who have never had the pleasure of navigating federal bureaucracy, what is SAM.gov?
SAM stands for System for Award Management. It is the central nervous system of U.S. government spending. If the government buys a pencil or an F-35 fighter jet or a consulting service, that transaction lives in SAM. It's the public ledger of the federal checkbook.
Okay, so we are looking at a dashboard for T.L. Tedford Enterprises.
Yeah.
And my eyes go immediately to the first column, total contract awards, and the number is 0.
0. A big round 0.
If I'm an investor, or even just a curious observer, 0 looks like a failure. It looks like they haven't sold a single thing to the government. My first thought is, this is all talk.
And that is exactly where a casual observer gets it wrong. You have to look at the whole dashboard. If you slide your eyes to the right, look at the column labeled Total Subcontract Reports.
Okay, I see it. It says 101.
101, that is the smoking gun.
Well, is 101 better than 0? And what is a subcontract report? I mean, it sounds less important than an award.
It sounds less important, but in this context, it's infinitely more important. To understand this, we have to understand how Washington actually works. We have to follow the money flow from the top all the way down.
Okay, walk me through it. Assume I know nothing.
Step 1. Congress passes a bill. Let's say the House and Senate pass the big annual Defense Authorization Act or an infrastructure bill. The president signs it. It's on the news. Everyone cheers.
Okay, so the money exists, conceptually.
But the money is sitting in a massive bucket at the Treasury. Step 2. The money is appropriated to an agency. Say the Department of Defense gets a slice, or the Department of Transportation gets another.
So it's been moved from one big government pot to a slightly smaller government pot. Still no contracts.
Still just a bucket of money. Step 3. The agency hires a prime contractor. These are the giants: Lockheed Martin, Raytheon, Northrop Grumman, Boeing. The agency gives them a massive contract, say $5 billion to build a new communication network. That shows up in SAM.gov as a prime award.
And Tedford has 0 of those. So they are not the prime.
Correct. They are not the ones shaking hands with the general at the press conference. But, and this is the crucial part, step 4, the prime contractor cannot do everything alone. Lockheed Martin builds planes. They don't necessarily manufacture the specific quantum sensor or the mesh networking code that goes inside, so they hire subcontractors.
I see where this is going. The primes hire specialists.
Exactly. When a prime hires a sub, or when a sub hires another a tier 2 subcontractor, they have to file subcontract reports to the government to track the spending and compliance.
So one-on-one subcontract reports means that T.L.TEDFORD is embedded in the supply chain of the prime contractors.
Deeply embedded. You don't file 101 federal reports for a hobby. That number implies volume. It implies complexity. It means that somewhere, a prime contractor with a massive award from the DoD or DOT has hired Tedford to do 101 distinct pieces of work, or is reporting on 101 flowdowns.
So while the front page says 0 awards, the back office is churning out 101 different reports.
Okay.
Could those just be tiny, meaningless reports, though? $100 here, $1,000 there?
It's possible, but unlikely. 101 is a very specific number. It's not 10, it's not 20. It suggests a high level of administrative activity consistent with being a key supplier on a large, complex program. It implies that money is moving, contracts are signed, and work is being performed.
And this connects back to their whole business model.
It connects directly back. Think about the hardware-agnostic nature of the node again. If your strategy is to be the intel inside, to be inside every car, every drone, every pavement slab, you don't want to be the prime.
Why not? I would think being the prime contractor is the goal.
Because if you are the prime, you are a competitor. If Tedford tried to build their own drone, they'd be competing with Lockheed or Boeing. But if they are a subcontractor providing the mesh to everyone,
then they are a partner.
they're a partner. They can sell to Lockheed and Boeing and Raytheon. They're not picking a side.
They are selling the shovels in the gold rush.
They are selling the dirt the shovels dig in. They are the infrastructure.
This connects back to the funding process you mentioned. We hear about the House and Senate passing these huge bills, but we rarely see the result at this level.
This screenshot is the result. That 101 represents the operationalization of those bills. The legislation passed months or years ago has finally trickled down through the bureaucracy, through the agencies, through the primes, and is now hitting the bank accounts of the companies actually bending metal and writing code.
So if you want to know if a technology is real, don't look at the press release. Look at the subcontract reports column in SAM.gov.
It's the boring, gray truth. But it tells you that the gears are turning. The infrastructure is being laid administratively right now.
That is fascinating. It completely flips the interpretation of that document. It goes from they have nothing to they are everywhere.
They are everywhere is the perfect segue to our final section, the implications. Because if this works, if they really do put these nodes everywhere, what kind of world are we building?
Section 5. Ethical and societal implications. The disclosure framework makes a big deal about planetary benefit. Is that just PR spin?
It could be, but I think we should take that at face value for a moment. The document talks about bringing connectivity to underserved populations.
The digital divide. It's a huge problem.
Right. Think about remote villages in the Amazon or rural communities in the mountains. Verizon isn't going to run fiber optic cable there. It's too expensive. There's no profit.
But the mesh.
The mesh doesn't need cable. If you drop a few solar-powered nodes in the ground and they daisy chain to a gateway 50 miles away, suddenly that village is online. The document says, not designed for exclusivity, it is designed for planetary benefit.
It democratizes access. You don't need to live in a city to have infrastructure.
That's the humanitarian case. And it's compelling. It's robust infrastructure for disaster zones. If an earthquake knocks out the power, the mesh running on batteries and solar might be the only thing still working.
But then there's the flip side, the control. We talked about physics over AI,
Yeah.
but the document also uses the term agentic intelligence.
Agentic. That's a word that makes ethicists nervous.
Agentic means it has agency. It can act on its own.
Yes. Currently, most AI is passive. You ask ChatGPT a question, it answers, doesn't do anything unless you ask. Agentic AI observes the world and takes action to achieve a goal.
In this case, the goal is
What?
keeping the network alive.
Optimizing the flow, preventing collisions. If the AI sees a traffic jam forming 5 miles ahead of you, it might reroute your car and every other car before the drivers even know there's a problem. That's agency.
That sounds great for traffic, but it requires surrendering a lot of control to an algorithm. Who sets the goals for that algorithm?
That is the multi-trillion-dollar question, and that's why the safety governance section is so important. We talked about signaling uncertainty.
The I don't know feature.
I cannot stress enough how important that is ethically. The biggest danger of AI isn't malice. It's incompetence masked as confidence. It's the yes man problem. If the grid is overloading, a bad AI might try to fudge the numbers to make it look green because its goal is keep status green.
Until the transformer explodes.
Right. A system designed to signal uncertainty is ethically bound to raise its hand and say, I am confused. The physics is ambiguous. Human, take over. It counters the black box fear. It keeps humans in the loop for the critical edge cases where judgment is required.
It feels like a very mature approach to AI. It's not promising magic. It's promising a very smart, very cautious partner.
Which is exactly what you want when you are dealing with critical infrastructure. You don't want a move fast and break things approach when you are managing the power grid or the highway system.
So let's bring it all home. We have covered a lot of ground today.
We have a lot of ground and a lot of water.
We started with the fragility of our current world, the house of cards built on GPS. We looked at the solution, the node, a hardware-agnostic, edge computing brick that uses physics to keep us safe.
We looked at the architecture, the living ground mesh, a network that flows like water over land and under the sea, healing itself when links are broken.
We looked at the market validation, the Royal Navy, proving that this kind of decentralized mesh is the future of survival in warfare, validating the entire doctrine.
And we looked at the paperwork, the 101 subcontract reports on SAM.gov that prove the funding is flowing and T.L.TEDFORD is embedded in the machinery of government contracting.
It's a converging picture. When you stack these sources, what's the one big takeaway for you? The so what?
For me, it represents a fundamental transition in the history of technology. We are moving from the era of centralization to the era of decentralization.
From the skyscraper to the mesh.
Exactly. For the last 40 years, we built big, fragile things. Big towers, big server farms, big satellites. If the center holds, we are fine. If the center breaks, we are lost.
And now?
Now we are building the grass. We are building a system where intelligence is distributed everywhere. It's smaller, it's quieter, but it's infinitely more resilient. It's the difference between a system that breaks and a system that heals.
That's a hopeful thought. But I have to go back to that one eerie feeling I had at the start.
The environment watching us.
Yes. If this works, if we really do get to centimeter awareness across the planet.
It is the final provocation. If every piece of pavement, every buoy, every streetlight is a node, then the world is no longer dead matter. It's alive with data. We are looking at the end of getting lost.
It sounds great.
It is great. But we are also looking at a world where the environment itself is watching and measuring everything. The road knows how fast you were driving. The walls know you were there. We are building a planetary nervous system. And once you turn on a nervous system...
it starts to feel.
Exactly. The question isn't just, does the tech work? The question is, are we ready to live inside a machine that is awake?
Something to mull over the next time you ask your phone to take you home. Thank you for joining us on this deep dive.
Always a pleasure.
Keep diving deep. We'll see you next time.